All right, section 3.5, we want to estimate the difference between two population average. So sometimes we want to see if one population average is significantly different to the second population. We can use this section to assess. But given that the two distribution or the two population, they are independent. So y1 minus y bar, or y1 bar minus y2 bar is exactly as mu1 minus mu2. We can use y1 bar from the sample, subtract to the sample y2 bar to estimate the difference. And since they are unbiased estimator, so the expected value, so there's missing a bar on top of the little y1 here. So expected value of y1 bar minus y2 bar is exactly as mu1 minus mu2. They are the unbiased estimator. But since the two populations, they are independent, the variance of the difference is indeed the summation of the variance of the y1 bar plus the variance of y2 bar. Okay, so it depends on whether we have the true variance or we can use the estimated variance. Okay, so that's the formula for the estimated variance. So let's look at example 3.12, the issuing of earnings report. So during the earnings reporting seasons, usually we have some of the larger firms and the smaller firms, they report their earnings during the year or half year. We want to see if there's significant difference of their earnings or the mean earnings among the larger firms or the smaller firms. So that's usually we apply that for in this financial markets to look at the big cap firm or the smaller capitalization firms, right? So we have the population size of 10,000 large one and 30,500 of the smaller firms. Usually they're measured by the market capitalizations in the financial market. So we obtain a simple random sampling. We only take 2001 large firms out of the 10,000 and 1,882 smaller firms out of the 30,000 firms. And then we calculate the Y bar for the large firms and the smaller firms respectively. So we want to see whether they are significantly different, statistically saying, right? So we also obtain some of the variations. To estimate the difference between the two mean durations of the large and small firms, so y1 bar minus y2 bar, that is 1.9. So we want to see if that 1.9 is significantly different. So whether if we are looking at these figures, is significantly different from 0, right? So we also calculate the standard error of the both. Then we calculate the variance of the differences of the two mean earnings. Actually, we need to add up the variance of the two means. So we have 0.4862 square. If we are not exclusively specified what is the confidence level or significant levels, we usually use 95%. So the bunch of error is 1.96 multiplied to the standard error, so which is the square root of the variance. So that's about 0.9529. So 1.9 plus or minus 0.9529. So we can construct a confidence interval. If the confidence interval, very likely they are greater than 0, so that is significantly, that 1.9 is significantly different from 0, so we can say that the mean earnings of the large firms is significantly different from the smaller firms. Okay, if the number of firms on the study are only known to be large compared to the sample size, what's the difference? So if that's the case, our sample size is relatively small as compared to the total population. So we can try to ignore 1 minus f. We can recalculate the variance. Now we have a slightly larger variance value because we are omitting the finite correction factor, right? So if that's the case, like we said earlier, it's very much similar to the infinite population case. The variance that we want to calculate or estimate for our mean difference is slightly larger than the previous one. Okay, and as a result, the error bound, the bound of error is also slightly wider. 3.6, estimation of the population proportion. That would be the third parameter that we usually want to look at to describe about the population. So given that we have a population of n units, and they would be given us some of the answer of, usually if we are asking for the yes/no question, if the answer is no, then we have a 0 enter. If the answer is yes, then we enter 1. So this is very convenient, so that at the end of the day, we know that if we just add up all the collecting data, either from the population or from the sample, and that would be the number of those saying yes, and then we simply divide by the n, the population size, then we can estimate we can find the proportion, right? So capital P, capital Q would be the proportion of yes, proportion of no, or 1 minus P. Let's take a simple random sample, randomly selected from the populations. So we would have y1, y2, or up to yn. Or we can say little p would be the sample proportions of 1. Q would be the sample proportions of the answer of no. The population proportions, so that equals to the summation of all of the answers, yi, adding up, divided by n. That equals to mu. Sample proportions, similarly, we add up all of the yi answers and divide by our sample size. Variance for the proportion can be further simplified because all of the yi's, they are now either having a 0 and 1 value. So yi square is indeed yi. Sigma square, the true population variance, equals to summation of yi square minus ny bar square divided by n. So yi square is actually yi. So this is actually adding up n number of yi, which is p, and we have n times y bar, which is also equals to the true proportion p. So we have np minus np squared divided by n, taking out or cancel out the capital N. So the variance of the population is p times 1 minus p, and we all knew that, and you should this should look familiar to you, because we know that the variance of yi is indeed equals to p times 1 minus p. For sample variance, sy square, again, this is a sample, so we divide by our sample size n minus 1. Similarly, we have summation of yi minus ny bar squared divided by n minus 1. Now we would have taken out the n, and then we have the n divided by n minus 1, p times 1 minus p as the estimate of our variance of our populations, or our samples. So for finite population case, the variance or the true variance of our proportion is equals to sigma square over n multiplied to the finite population corrections. So for the proportion case, sigma square, we just find that sigma square is equals to p times 1 minus p. So that would be the finite population correction factor multiplied to p times 1 minus p divided by n. Okay, so this is a true variance of our sample proportion. So, but given sigma square is known, that is similarly saying that given the population proportion is known. And if sigma square or the population variance is not given, then we can use the S square to estimate the estimated variance. So estimated variance of our estimated proportion is equals to the final population correction factor multiplied to sy square over n. So similar to what we did in measuring the y bar, right? But in this case, s square is equals to n over n minus 1, p times 1 minus p. Okay, so we can cancel some of the common factor like the n. So in this case, we have 1 minus f little p from our sample multiplied to 1 minus p and divided by n minus 1. Okay, so beware with the estimated variance with a hat on top, estimated variance of our sample p. Now we have to we find that equals to the final population correction factor multiplied to our point estimate proportion times 1 minus proportion divided by n minus 1. Okay. So example 3.13, the simple random sampling of 100 college seniors was selected from the populations. So we want to estimate the proportion of seniors going to graduate school and the proportion of seniors that held part-time jobs during the college. So yi, xi are 15 out of 100, 65 out of 100. So easily p would equals to 15% or 0.15, px equals to 65% or 0.65. Okay, and we can estimate the standard error, which is the estimated variance of our proportion. So estimated variance of our proportion, we use the simple random finite population correction factor multiplied to the sample p times 1 minus p divided by n minus 1. We are using this because the true population proportion is not given. Okay, so taking the square root of the estimated variance, we find the standard error of our point estimate, both for y and x. Next, a study on the extent of absenteeism that are not connected with illness or official holidays. So this is the previous example. Now we want to say that on average, the number of days of the worker has taken off is about 1.296, and then we calculate the variance previously. Now, we want to say that if the worker is taking more than 3 days in 6 months, is regarded as unreasonable. So we want to look at what is the proportion of those are taking more than 3 days. Okay, so we add up starting from 4 days. So in 49, 21, 5, 11, 2, 0. Out of that, 88 out of 1,000 workers actually has taken more than 3 days leave. And then we say this is unreasonable. So how about 0.08 or 8% of those are unreasonable? Then we want to construct a 95% confidence interval to explain how confident you are going to conclude 8% of the workers are taking unreasonable leave. So 8% plus or minus our margin of error, right? So that equals to 1.96 multiplied to the square root of estimate of the variance of our P.